Welcome to Simponics. In this video series, we'll learn how to program the BACnet IP protocol on the STM32F103 microcontroller. You'll explore how BACnet IP works, how to build its communication stack from scratch, and how to make your STM32 device communicate with other BACnet devices in a building automation system. Each episode will walk you through a specific part of the process. From protocol basics, UDP socket handling, and APDU message structures, to practical testing with BACnet tools and simulators. Whether you're an embedded engineer, automation developer, or student, this series provides a clear, hands-on learning path. By the end of the series, you'll be able to create your own BACnet IP-enabled controller based on STM32, ready for integration into real building management systems. Right finger subscribe to Simponics and follow the playlist to keep learning and building smarter systems. The BACnet protocol, short for Building Automation and Control Network, was developed by ASHRAE in the late 1980s. Its goal was to create an open communication standard that allows devices from different manufacturers to work together seamlessly in building automation systems. In 1995, BACnet became the ANSI ASHRAE Standard 135, and by 2003, it was adopted as the international standard ISO 16484-5. Initially, BACnet used -485 rupees in Ethernet, later evolving into BACnet IP, enabling communication over modern IP networks. Today, BACnet continues to grow with BACnet Secure Connect, providing encrypted and secure communication for the IoT and smart building era. As of now, BACnet connects over 1.42 billion devices worldwide, supported by 11 active technical committees, and integrates with more than 928 million IoT-enabled devices. Today, BACnet stands as the world's leading communication protocol for building automation and control. It acts as a universal language that connects thousands of devices from different manufacturers, allowing them to share data and work together seamlessly across the same network. BACnet is now deeply integrated into almost every building management system, including HVAC systems, controlling air conditioning, ventilation, and climate comfort, lighting systems, enabling smart and energy-efficient illumination, fire alarm and life safety systems, ensuring fast and reliable emergency response, security and access control, managing cameras, alarms, and door locks, electrical and power distribution systems, elevator and escalator control, water supply and pumping systems, renewable energy systems, such as solar inverters and energy storage, parking management and charging stations, and even IoT gateways and cloud-based analytics. With its open, scalable, and secure architecture, BACnet continues to evolve as the backbone of smart buildings and smart cities, connecting over 1.42 billion devices worldwide and driving the future of intelligent infrastructure. In this project, I will use the following software tools and hardware components to develop and test the BACnet IP protocol on the STM32F103 microcontroller. On the software side, the project uses STM32CubeMX to configure peripherals, set up system clocks, and generate initialization code automatically. Kyle Micro Vision, ARM Kyle C, as the main IDE for firmware coding, debugging, and compiling the BACnet stack. On the hardware side, the setup includes a development board with the STM32F103 chip, which serves as the main BACnet device, an ST-Link V2 programmer debugger, used for flashing and debugging firmware, W5500 Ethernet module, providing the TCP/IP interface for BACnet IP communication. For testing and verification, I will use Wireshark to capture and analyze BACnet IP packets at the network level. YABE, yet another BACnet Explorer, to discover BACnet devices, browse objects, and test communication. STM32 CubeMX configuration. In this part of the project, I will configure the STM32 microcontroller using STM32 CubeMX. First, I create a new project by selecting the STM32F103 RCT6 chip from the device list. This microcontroller will serve as the main controller for the BACnet IP implementation. After creating the project, I begin with the RCC, reset and clock control, configuration. I enable the high-speed external HSE oscillator, allowing the system to use an external crystal as a precise and stable clock source. Next, I enable the serial wire debug SWD interface under the debug settings. This provides firmware programming and real-time debugging capability using the SaintLink v2 programmer. Then, I enable the SPI1 peripheral in full duplex master mode to interface with the W5500 Ethernet module, used for BACnet IP networking. I also assign the PA4 pin as the chip select CS signal, which controls communication between the STM32 and the Ethernet module. After completing the peripheral setup, I configure the system clock to run at 72 MHz, which is the maximum stable operating frequency for the STM32F103 series. Once the clock configuration is complete, I go back to review all the previous settings. At this point, I notice that STM32 CubeMX shows a warning on the SPI1 peripheral. I click on the warning to verify and fine-tune the communication parameters. Here, I adjust the SPI1 prescaler to 4, which sets the SPI communication speed to approximately 18 megabits per second, providing a stable and fast data transfer rate for the W5500 module. Finally, I move to the Project Manager tab. In this step, I set the project name, define the storage directory, and choose the toolchain IDE, which in this case is Keil Micro Vision. After confirming all configurations, I click Generate Code to create the initialization files and HAL-based project structure by clicking the Generate Code button. STM32 CubeMX starts creating the source files and project structure based on our configuration. Once the generation is complete, a confirmation dialog appears. Here, we select Open Project to automatically launch the generated project in Keil Micro Vision. MDKR-MIDE. When Keil opens, we can see the complete project folder with initialization files, driver libraries, and configuration code already generated. In this stage, we take a moment to verify the project structure, check that the necessary files have been included correctly, and confirm that there are no configuration errors. Finally, we perform a build test inside Keil to ensure the code compiles successfully without any errors or warning. We continue from the previous step where the STM32 project was successfully generated using CubeMX. We move on to setting up the Keil CIDE and preparing the workspace for BACnet IP development. After that, we integrate the required libraries, including the Ethernet W5500 driver, ensuring proper support for BACnet IP communication. Finally, we perform the initial configuration needed to establish a clean and reliable foundation for building a BACnet IP application on STM32. Next, we create a libraries folder inside our project and add a W5500 subfolder. This helps keep all the Ethernet driver files organized and easy to manage. Step 1. Go to GitHub and download the official W5500 driver library. This package has all the source files we need to get the W5500 module working with STM32. Step 2. From the downloaded library, we pick the key files for our project and copy them into the W5500 folder. Here's what we focus on. Socket. C. This is where all the socket functions live, like opening, closing, sending, and receiving data via TCP or UDP. WizChip_conference H. This header sets up the configuration for the W5500 chip, like SPI callbacks, buffer sizes, and hardware control. W5500 C contains the low-level functions to read and write registers on the W5500, basically letting the STM32 control the Ethernet hardware. These files are the backbone of the communication between our STM32 and the W5500, making it ready for BACnet IP networking. Next, let's integrate the W5500 library into our Kyle project. Step 1. Click on the Manage Project Items button in Kyle. This opens the project structure where we can organize our source files. Step 2. Create a new group and name it Ethernet W5500. This group will hold all the files related to the W5500 Ethernet module, keeping the project organized. Step 3. Add the 3 main library files into the group. Right-click on Ethernet W5500, right-pointing arrow, add existing files to group. Then select Socket, C, W5500, C, and WizChip_conference H. These files provide the core functions for Ethernet communication. Step 4. Configure the include paths so Kyle can find the header files. Go to Project right-pointing arrow options for target right-pointing arrow C, C++, and add the path to your library's W5500 folder. This ensures that all headers like WizChip_conference H are correctly referenced during compilation. Now it's time to build the project and make sure everything is working correctly. Click on the Build button in Kyle and watch the compilation process. If there are no errors or missing references, congratulations! The build is successful. This means the W5500 library is fully integrated, and your project is ready to move on to SPI configuration and BACnet IP development. Next, we'll configure the SPI interface and set up UDP communication for the W5500 Ethernet module, which is essential for BACnet IP. Step 1. Open the SPI H file. Define the Ethernet buffer size and the W5500 socket numbers. Define Ethernet_data_BUF_size 2048. Enum W5500 socket define. TCP _SOCNUM equals 0. UDP _SOCNUM equals 1. HTTP _SOCNUM equals 2. DHCP _SOCNUM equals 3. Max _SOC _num equals 8. This sets up a 2 kilobytes buffer and symbolic names for TCP, UDP, HTTP, and DHCP sockets, making it easier to manage multiple sockets in your project. Step 2. Open the SPI.c file. Declare the shared Ethernet buffers for transmitting and receiving data. These buffers temporarily store incoming and outgoing Ethernet data, allowing the STM32 to communicate efficiently with the W5500. Step 3. Implement the core SPI and W5500 functions in SPI.c. Chip select, unselect, SPI read, write functions. Initialization function. This function initializes the W5500 chip. It configures the IP address, MAC address, and subnet mask for the module. MAC, EA, 11 hours 22 minutes and 33 seconds, 44, EA. IP, 192.168.68.111. Subnet mask, 255.255.255.0. Step 4. Configure UDP sockets for BACnet IP. Initialize UDP socket. Opens a UDP socket on a specific socket number and local port. BACnet IP typically uses 47808. Prepares the W5500 to send and receive UDP packets. Receive UDP packets. Continuously checks for incoming UDP packets. Reads data from the W5500 RX buffer into a local buffer for BACnet processing. Why this is important? BACnet IP runs entirely on UDP. So initializing the UDP socket and handling incoming packets is essential for communication with other BACnet devices. Step 5. Go to the main.c file and initialize the W5500 module by calling the init_W5500 function. This sets up the IP address, MAC address, and subnet mask for the W5500. It also registers the SPI and CS callbacks and prepares the Ethernet buffers. After calling this function, the W5500 is fully initialized and ready to communicate over BACnet IP. Step 6. Now, build the project in Kyle and flash it to your STM32 board. In this video, we tested the W5500 by pinging its IP address from a PC, and it responded successfully. This confirms that the W5500 is correctly initialized and communicating on the network, making the project ready for BACnet IP development. Conclusion. That wraps up this video. We've successfully built the project and tested the STM32 board with the W5500 module. Everything is working perfectly. The module responds on the network, confirming our Ethernet setup is fully functional. In the next video, we'll take the next step and dive into the BACnet stack, exploring how to implement BACnet IP communication on top of our W5500 setup. Make sure to stay tuned for that.